or osmosis. All right, I have included this slide. I don't think it's on your lecture slides if you like download them from Blackboard or print them out. I've added this because I want you to practice calculating osmolarity. Okay, and I put this statement up here with 2 asterisks saying when calculating osmolarity, the main thing you need to ask yourself to simplify all this is how many particles or ions, and again, you can't always say ions because some particles or some molecules do not break down into ions. Okay, so if it's not an ionic compound, then you're just asking how many particles am I going to get here. But if it's an ionic compound, a good way to think about it is how many ions or how many different particles will this compound produce when dissolved in solution. So we're going to calculate the osmolarity of these following solutions. We have on the first one 0.5 molar potassium chloride. Okay, so let's ask the question, this is an ionic compound for sure. We should recognize that. We have K plus and Cl minus. I'm going to zoom in a little bit. How many particles, if we put this into solution, how many particles would it break down into? Well, we know if we have, or it would break down into 1 K plus, and it would break down into 1 Cl minus. Okay? So if we have 0.5 molar, which is 0.5 moles of KCl per liter, then we have, when it's in solution, we're going to have 0.5 K plus particles per liter, and, or I should say plus 0.5 Cl minus particles per liter. Okay, so now we just add those up because osmolarity is the total number of moles of particles per liter. So we're going to get half a mole. I forgot to write in moles. Okay, so it should say moles, and right here I should have written moles. Okay, so we're going to add that up. In total, we will have 1 mole of particles. Per liter. Okay, we don't care about the identity. Now, we did identify them up here as potassium and chloride particles, and we needed to do that to analyze how this compound KCl will break down. But when you're writing just the concentration of osmolarity, we don't care that it's potassium chloride. We just care about the total number of particles. So half a mole of potassium particles plus another half a mole of KCl particles is 1 mole per liter, which is 1 osmole. So the answer here, calculate the osmolarity, we have 1 osmole. All right, let's do the same thing with calcium chloride. If it breaks up into ions, if we have 1 molar, we will get, for every 1 mole of calcium chloride, or 1 molecule I should say, for every 1 molecule of calcium chloride, how many calcium cations, how many chloride anions would you get? We would get 1 calcium, I need to capitalize that, 1 calcium cation, and we will get 2 chloride anions. So if we have 1 mole per liter of CaCl2, we are going to have 1 mole of Ca2 plus particles per liter. The volume hasn't changed. Plus, we're going to have 2 moles of Cl minus particles per liter. So we just add those up. 1 mole of calcium particles, 2 moles of chloride particles, total equals 3 moles of particles per liter, which equals 3 osmoles. Okay? So that was our answer there. Lastly, what about if we have a solution that is 3 molar glucose, if we put glucose in solution, if I have 1 molecule of glucose, how many particles will I get? Well, it's not an ionic compound, it's not going to break down into ions. So for every 1 molecule of glucose, I will still get 1 molecule of, I'm going to abbreviate, capital G, glucose. It will not break down any further into smaller particles. So if I have 3 moles of glucose per liter, then I have 3 moles of glucose. We are calling glucose a particle at this point because it is the smallest unit. It will not break down any further per liter. So if I have 3 moles of glucose particles per liter, I have 3 osmoles. Okay, that was our answer there. Okay, so I hope that's helped to clarify how do you calculate osmolarity. But we are going to move on to kind of our last 2 big ideas with osmosis. I wanted to give you kind of a real example of why osmosis is important and how we see it play out with like blood and red blood cells. If you look at these pictures, the first picture, I'll say picture number 1, is normal blood cells. Okay, these are, if you read down here at the bottom, red blood cells in isotonic solution. What that means is that the solution inside the red blood cells has the same osmolarity as solution outside red blood cells. Okay, the solution inside, when the solutions are isotonic inside and outside the blood cells, then we have the same osmolarity of particles. What kind of particles are we talking about? Lots of different particles in blood and intracellular, extracellular fluid. There's proteins, there's electrolytes, all kinds of stuff. But essentially what we need to know is there is no gradient. There's no gradient here when the solutions are isotonic, and you get these nice donut-looking red blood cells. Okay. If you look at the picture number 2, middle picture, these blood cells look swollen. Okay, compared to picture number 1, and these are red blood cells in what we call hypotonic. Okay, solution. So what that means, hypotonic solution. That means the solution inside the red blood cells has higher osmolarity than solution outside the red blood cells. The solution inside the red blood cells has a higher osmolarity than the solution outside the red blood cells. And what that causes is this solution out here is going to rush in. Let me pick a different color. Maybe like will bright green work? Should I do really dark? Will white work? Yeah, that works. The solution, because there's a gradient and the higher concentration is inside, the higher osmolarity is inside the red blood cells, then the solution or the solvent particles are going to move from outside the red blood cells to inside the red blood cells. So all the solution surrounding these red blood cells is going to rush in, and that's what causes the red blood cells to swell up. So there's a gradient here. There's a gradient that causes fluid to enter red blood cells in order to lower the osmolarity. Okay. Lastly, picture 3. Here you have these terrible looking shriveled red blood cells. These are red blood cells in what we call a hypertonic solution. Hypertonic means that solution inside the red blood cells is or has a lower osmolarity than solution outside the red blood cells. Hypertonic means it has a higher osmolarity. Hypotonic means it has a lower osmolarity. And we're talking about the solution outside the red blood cells. So in picture number 2, the solution outside the red blood cells had a lower osmolarity. Here in solution number 3, the solution outside the red blood cells has a higher osmolarity, okay, compared to the solution inside the red blood cells. So this also sets up a gradient. I keep misspelling this. That causes fluid to leave red blood cells and rush out of the cells. So if we draw a picture here, fluid would be leaving the red blood cells, rushing out into the surrounding area to try to even the osmolarities, okay? To try to dilute the outside solution, which has a higher osmolarity, so we want to dilute it to try to make the solutions isotonic. That's the goal, okay? So that is why solution leaves the red blood cells, and the red blood cells then look shriveled compared to normal red blood cells. So I definitely want you to understand isotonic, hypotonic, and the term hypertonic. I want you to understand what kind of gradient that would set up and how solvent would move from a solution that is hypotonic